Hi everyone, my name is Sunil Kumar. I'm a graduate from IIT Kharagpur. I've done my BTech as well as MTech in chemical engineering. I have been associated with askIITians as an in-house faculty for mathematics. Now, today what we are going to do is, we'll look at the lecture based on the topic application of derivatives. Now, till now, you have studied differentiation, limits, derivatives, continuity and differentiability, right? Now, what we are going to do in this part is, we'll look at the application part. Now, when we talk of application, we basically are going to understand why did we learn all these topics, right? So, in this part, we'll be starting with monotonicity. After that, we will be going on to study maxima and minima, and in the next part, we'll be studying tangents and normal. In the final part, I have kept a segment called miscellaneous. Basically, everything else that requires the application of derivatives is included in that. Now, we'll be starting off with part 1, where we'll be studying monotonicity. In monotonicity, basically, we'll look at functions in with an objective to see where it lies on a graph sheet. So, when we'll be studying this, how the function is increasing, how is it decreasing, and where is the point of inflection, basically from which part the function starts increasing and where it starts decreasing. So there are different parts in that. So we'll be studying monotonicity as the first part. Now in this part, we'll be looking at the chapter application of derivatives. In this chapter, we are going to process everything that we have studied in derivatives and look at how we can apply it in our real lives, in our day-to-day working or in the complex matters where we need to simplify things using derivatives. Alright, now starting on, what are the topics that we will be studying under this category? First of all, monotonicity. Okay, next is maxima and minima, then tangents and normals, and there is a part which I would like to call as miscellaneous application, which contain different aspects like its application in physics, maybe chemistry, or also in economics. Next part would be, we'll be looking at the direct problems which have previously come in IIT-JEE questions. Alright, now starting on first of all with monotonicity. Now, in this part, what is monotonicity? Okay, first of all, you need to know this part, mono. Okay, in general, you might have heard about the term monotonic, right? What does monotonic defines? Okay, what are monotonic things? Similar to that, when we look at a certain function, let's say, we are looking at a function, okay, the similar nature that is defined in a monotonic life, it is defined in terms of functions. Alright, let's look at the live examples. Let's say a sun rises, right, every day early in the morning, right? So this is our sunrise. Alright, then I have my sunset. Alright, my sunset comes every day, right? So this is a daily occurrence, right? This is my daily occurrence. Now, from the time you were born and probably up to the time that you die, this is one monotonic function that will always occur, right? Every day in the morning the sun will rise, okay, and every day in the evening the sun will set. Now, but what changes during an year, right? That is the part which we are going to be focusing when we study monotonic functions. Alright, let's look at it this way. Alright, now the sun rises and sun sets every day, right? But it varies during different seasons, right? Let's say, for example, when our winter comes, alright, when a winter comes, the sun rises late, right? every day, and the sun sets early. So the time duration of the daylight decreases, right? Moving on, when we go into an spring, when we go into a spring, then the time duration of the sun increases, right? The daytime increases. Alright, moving forward comes to the beautiful summer. Alright, now the summer may not be beautiful to a lot of the countries where it is mostly humid, high heat, okay, and there will be hot air blowing everywhere, right, with a maximum temperature sometimes reaching up to 50 degrees. But what is the most important area over here? The sun time. The time duration of the sunlight increases. It is maximum during the summer, right? Moving on, in the next part we come is the rainy season. Now this part, the sun comes out for a longer period of time, okay, not more than summers, it is definitely lesser than summer, but you're never sure whether or not the sun is out or not, right, because you'll have cloudy days, right, so you will not be able to make out. But even during that period, the sun is out for a definite amount of time. And then finally we have our autumn, right, and during this autumn also the amount of sunrise varies from rainy season. Now, what are the two things that we have seen till now? That the sun rises and the sun sets, for fact, but the time duration for which it is there in all these different seasons, they vary. Alright, now if you look at it, there are only two instances where they may be same. It would be during the spring and in the autumn. During these two periods, the number of hours for a sunlight and the darkness, that is the night time, would be same. Alright, so this is how we see, if you look at one particular aspect, let's say the sunlight, it is minimum over here during the winter time, right? It increases in the spring, it is maximum during the summer, it is lesser when it comes to rainy, then in autumn it is equivalent to the spring but lesser than the rainy season, and then again it reaches to this minimum. Now, why understanding this is important? This is a natural aspect. Let's say during my winters, the sun comes out for 8 hours. Alright. Now this varies with equator, you know that, okay, it's part of physics, part biology, you will be knowing that. Okay, here I am taking numbers just for the sake of understanding. Alright, let's say during the spring it's for 10 hours. In summers it increases to as much as 12 to 14 hours depending on where you stay. Then again in the rainy season it is somewhere around 9 to 10 to 11 hours. Alright, nobody is sure, but it is less than this. Alright, that's for sure. Then again in the autumn it is for 10 hours. So you see, if you draw a graph for this, alright, if you draw a graph for this, it will vary in a way where it will start with the winters. Let's say I start with winter, spring, summer, rainy, and then autumn. Alright, and then it comes back to winter. Let's say I start from here, so it increases, right, then again it increases over here, it decreases to a certain degree over here, then again it decreases over here, and then again it comes back to this level. Now what is important is this, that you see during the spring at this part and during the autumn at this part, this level is the same roughly. Alright, so this is the part that when we study monotonicity, this is the area where we focus. Okay, what is the maximum R? See, this is the maximum, right, and this is my minimum R's. So these are the prime focus that we will be having. Now also let's look at it on our daily life. Let's say this is a general trend that we follow every day, right? We get up every day in the morning, shook up by our alarm clock, right? So we get up, we have our breakfast, we brush. Okay, this is not in a proper order, but let's say we brush our teeth, we go to our school, we take all our classes, we have our lunch, then we play, then we watch TV for some time with our evening snacks, then we do our homework, we struggle there, then our delight dinner is ready. Now this varies depending from people to people. We have a pre-nap shower, and then in the evening we doze off to our sleep late in the night. Now over here also, here this is something that we do every day, right? Again, I'm focusing on the part, the things that we do every day. Okay, now each day, okay, this is a variance. Each day it might so happen that in either of these 12 activities that is stated here, you might take the equivalent amount of time every day, or this time span may increase for particular days. Let's say when your exam times are coming, you reduce your time over here and over here, and this time increases, right? When your vacations are up, this increases, okay, this decreases, this and this obviously increases during vacations, and this goes down. Also during vacations, this is almost nil. It is exactly nil. Okay, so what happens, even as per our daily routine, we change our time duration for different activities depending on what is occurring, right? Let's say if we have school days, this is a regular schedule for that. If we have exams coming, your time varies for different activities. When you have vacation, your time varies for different activities. Now based on this only, the study of monotonicity was archived. When we first studied monotonicity, if all of this were to be defined in a function fx form, this is what all its study is about. Now let's look at how we define a monotonicity. Monotonicity is defined when a function is either increasing or decreasing, right? Like we saw in our daily activity, right? The time duration, it increases or decreases. Similarly, the function, it may increase or decrease. If a function is monotonic, if it is increasing or decreasing on an interval. Now, that interval that we talked, let's say your fixed amount of time you have for studies every day, right? But it increases during our exam time and decreases during our vacation time. So based on that, we come to know that a function is monotonic if it is increasing or decreasing during an interval. Now let's look at a graph. Okay, similar to this graph that I had just shown you, right? Over here, let's say our function at a particular part, it starts from here. The maximum it reaches over here, and this is the minimum that it reaches, and this is again some point. Okay, let's say this is the graph of your study time during an year. Okay, let's say when our school starts. All right, let's say this is our school starting. Then during the exam time, that is over here, this will be your peak number of hours you will give for studies. All right, then after the exam comes vacation. Then during that period, it is your minimum number of hours that you give. And then again, when the school ends, you go to the peak to study a lot more, and then it ends. Okay, now if you look at this whole part, okay, if I define this whole part, okay, how do I define it? This is my intervals. By intervals I mean the duration that we had from A from your school starting to the exam time. Okay, during that time, let's say your function was increasing, right? You saw your graph, it was going upwards, right? Then during the next part, that is from the exam to the vacation part, it was decreasing, right? Based on the curve how it goes, this is defined. Then again after the vacation during and to the next part of the exam, it was again increasing, right? So the function fx during the intervals a, b, c, d, okay, mentioned, it increases, decreases, and then it increases again. Alright, so this is the point that we studied, that there are different values for a function at different intervals. Let's say I define a particular function during an interval 4 to 5, assuming, okay, during a particular function, I say, let's say my function, it is given by, let's say, some 4x square minus 3x, okay. Now during a particular interval, now this is all complete assumption, 4 to 5, it might have some values, okay. Then again at an interval, let's say 8 to 10, it will have a different value, and then again from 12 to 15. Now during this period, this function, the values would be increasing. It could be increasing over here or increasing over here. You just basically have to check for what value. Let's say I keep the values over here, so I will have 16 for the 64 minus 12, I'll have 52 for f of 4, then f of 5, I'll have 100 minus 15 is 85. Now you see what is happening during this period, the value of this function is increasing, right? Now these all vary during all of these periods. Okay, that would depend on the function. You basically check for the values that during an interval, in which way the function behaves. Okay, all the functions can be plotted in a particular graph sheet. I am sure you are aware of it. So every function, if you put it on a graph sheet, based on that graph sheet, the value of x for which it achieves an increasing order, the function increases. The segment where it is in decreasing order, then it will be a decreasing area. Alright, so in different areas for a different set of values for different intervals that we call it, okay, the function may be increasing or decreasing. Alright, so that is the part. Moving on, let's say when we come to our functions, we have our first derivative test. Now, when we talk about first derivative test, you see this is an application part, right, of a function. So when we check for the first derivative test, what do we do? Okay, now let us say a particular function is said to be continuous in a particular open interval containing critical points. Now we'll come to the critical points in the next part, okay, but the important thing to know is that fx is continuous on an open interval containing a critical points. Let's say if my fx is differentiable, you have studied this part, on a particular interval except possibly at critical points, then fx at critical points can be classified as follows. Local maxima if fx changes from positive to negative at m, local minima if fx changes from negative to positive at n. If there is no sign change, then the critical point is not a local maximum or minimum. Now let's come to this part again by the same function that we used, the graph of it. Now what are the points that it said? Okay, now first of all, fx during a particular open interval, okay, a comma b, okay. Now at a particular point during this value, during this particular interval, Let's say I have my f of a and I have my f of b. Let's say it gives me a value a and b. Now my a would be greater than b, or my b will be greater than a, or it so may happen that a is equals to b. These are the three things that may happen. Now, with respect to what we have just looked at, the 3 points, these are the areas that we need to focus. Let's say at this point, okay, from let's say I consider the interval a to f, or let's say e to f. I take my interval from e to f for the function. Now in this area, you see the function behaves in such a way that there is some value that I get for f of e, there is some value that I get for f of f. At this point, you see this m, the value of the function takes its maximum point, that is its maximum value. Okay, this is what is called to be C, or the critical point, right? See, up till this, from here to here, if I go from here to this part, the function value, it keeps on increasing, right? But when I have achieved the maximum value, after that to the next part, the value starts decreasing, right? So there is a change that occurs from this part to this part, right? And it starts from this part, right? This is the critical point, right? So critical point is the point where the value, it starts, either it was increasing, right? And the point after which it becomes, it changes its value, that it comes down, it becomes decreasing. That is what is called to be the critical point. And that critical point will actually provide me this maxima, right? So this is the point where I achieve my maxima, right? Similarly, if I look at these two parts, my f and g, look at during this part, what is happening during this? You see my slope is going downwards, right? Now at this point again, you see over here it is coming down, right? So my values are decreasing over here during this area, right? But again, after it reaches n, it again starts increasing, right? So this again becomes a critical point, and this is where I achieve my minimum value. Alright? So when a function, it changes from positive to negative, the value of the function where it changes from positive to negative, that is the point of maxima, and the point at which the value changes from negative to positive, it becomes a minimum. Alright, so that was the whole point of studying this. Okay, now moving on to the next part. See, this is how we have defined, right, all that we have studied, right? Now to that point, f of n and f of m, right, those are what is said to be our local maximum points and local minimum points. The reason why we call it a local maximum, local minimum, because during the different parts of the function, the value, it may increase or decrease depending. But we restricted it to a particular part, and we took a local area, okay, the neighborhood area. So that is why we call it to be a local maxima or a local minima. Now, moving ahead, you see what is happening, okay, over here, right? When the function is differentiable, what is happen? It is positive, right? F dash x is greater than 0, the function is increasing. Alright, now at the test point f dash of f, if I take, there it was negative. Why it was negative? Because my f dash of x was less than 0. So the function at that point is decreasing, and I get my local minima there. Okay? Now, moving on, this is another part of the test. You see, based on our graph, we had an upward graph like this, and then we had a downwards graph, right? Based on that, I have a property called the concavity. Okay, let's say it defines basically the curvature of the functions, just as I told you. Alright, a function is concave upwards, okay, on an open interval if my f dash x is increasing on that interval. Alright, similarly, nothing different, just we are naming that particular local part or the interval with a particular name. Okay, if it is increasing function, then it is concave upwards. If it is concave downwards, then it is a decreasing function for f dash of x. Okay, and the point, the critical point is what is called to be the point of inflection. Basically, where concave becomes convex, that point is said to be the inflection point. Now, see over here from this part, you see this part, from this part onwards it started changing, right? Up till this point it was concave downwards, and from this part onwards it becomes concave upwards. So this becomes my POI, the point of inflection. Okay, moving ahead, I have my first derivative test. Okay, in the first derivative test, what did we see? The concavity of a particular function fx during a particular interval AC, it was concave downwards and then it was concave upwards. Alright, now let's move on to the next part where we study the second derivative test for local extrema. Now let's say I have my function. Okay, based on all those study only, if I have my f dash c equals to 0, okay, which it makes at a particular critical point, okay, like we defined, and my f dash c, this is the second derivative test, this is the important part, my f dash double dash c is less than 0, then f has a local maxima at x equals to c, just as I told you. Alright, the second derivative test has to fail, that is, it will become negative. If that so happens, then that is the point where my maxima is achieved. Alright, and inverse would be the case for local minima. If my second derivative is positive, then at that point I achieve my local minimum. Okay, so it is all advertly related to the first graph function that we studied. So based on that, if at a particular point, let's say at x equals to c, where my first, again look at this part, my first derivative has to be equal to 0, I equated it with 0, and then I check for my second derivative. If it is less than 0, then the function it achieves is local maxima at that critical point for that value of x equals to c, and inversely, if my second derivative is greater than 0, then at that point of x equals to c, I get my local minima. Now, there is an important keynote over here. If the second derivative is equal to 0 or it is undefined, then the second derivative test is inconclusive. And now the part of this, it is just for your knowledge. Okay, this is the application part of it is not for you to know. Okay, it is not within your syllabus for now, but there is something intriguing for that part. It so may happen that my second derivative may be something undefined or it may be equal to 0. So in that case, you have to broaden your spectrum, that is the interval. Okay, but that is again not for you to study. Alright, now see, so based on that I have this table. Okay, let's say if my second derivative is negative, it is concavity is concave down and it gives me local maxima. Second derivative test is positive, it is my concave upwards and I get my local minima. Now let's have a look at the examples based on the topic that we have discussed. Let's look at the first question. Our first question here says, is y equals to mod of x a monotonic on interval? That's given over here. Now for this question, what we will do is, we'll first plot a graph based on it. Okay, let's say I draw my graph. Now let's say I draw the graph over here. Okay, now for y is equals to mod of x, you see the graph would be like this, right? I draw it over here also, it will go like this, right, to infinity, right? This is my 0 and this correspondingly, this is my plus of y, this is my minus of y, plus of x and minus of x. Alright, now if you look at this, okay, you see in the domain that is from minus 1 to 1, in this domain what is happening? You see, in this domain the curve is increasing, right? It is increasing from minus of infinity to it is decreasing. Okay, increasing is from 0 to infinity, right? And this curve is decreasing in the interval of minus infinity to 0, right? So in the intermediate zone, that is from the zone that we need to calculate in this part, the function here first is decreasing from minus 1 to 0, right? And then it becomes increasing in the domain this, right? So in this case, this is not a monotonic function, not monotonic in the given interval. Okay, now if it were in the domain of, let's say 2 to, let's say this is 6 or 5, okay, if it were in the domain of 2 to 5, this function would have been increasing, right? But in this part, you see the function first is decreasing and then it is increasing, right? So it does not become a monotonic. If it were in this function, however, it would have been increasing and thus it would have been a monotonic function. Alright, now let's look at the next example. In the next question here, you need to show whether the function y is monotonic or not. Okay, basically it is given that you need to show that it is not a monotonic function. Now I have my y is equals to minus x plus 1 whole square, right? I can also write this as x minus 1 whole square, right? Now for this, what will be my domain? Okay, I need to first figure that out. Now in this case, if you solve it, its point of inflection is at x equals to 1, right? Similarly, in the graph, if you plot it, right, it will come down something like this, where x equals to 1, you will get the point of inflection, right? So again over here you see it is decreasing in the domain of minus infinity to 1, right, and increasing in the domain of 1 to infinity, right? This will be closed. Alright, so similar to the previous question, this is also not monotonic. Alright, had the case been similar, let's say if I took this domain, okay, let's say I took this domain, then over here I could have said that it is monotonic, but I am taking the domain over here is R. So first what I do is I define its domain. Okay, now this domain for this here R will belong with minus infinity comma 1 union 1 comma infinity. So during this domain it is not monotonic. Alright, so you see, based on everything that we have learned, this is how we need to first figure out the domain, alright, whether or not my equation follows the rules of the monotonic functions or not. Okay, here we studied monotonicity. Now up till this part it was only about increasing and decreasing of the functions. Okay, we took a particular interval and checked whether or not the function is continuous or not, etc. other topics. Now in the next topic what we'll be studying with is maxima and minima. Now over here we'll be going to the next step. Up till now we have studied first derivative. In this part we'll be looking at the two derivatives, that is differentiation over differentiation. So stay tuned with askIITians for the next part.